Computers talk to each other in binary, a continuous stream of zeros and ones. But moving that data across a network comes with physical risks. As you can see in this textbook excerpt, interference like electrical spikes or lightning strikes can actually cause a single bit to flip from a 0 to a 1 during transmission. That might sound like a tiny glitch, but flipping just one bit in a data sequence is enough to completely corrupt an image, a document, or a video file. Keeping data intact is a massive challenge for network reliability. To catch these errors, network engineers use a surprisingly simple tool called a Parity Bit. Instead of sending just a standard block of 7 bits of data, the system tacks on one extra bit at the very end of the sequence. That single extra bit acts as a security guard for the entire byte. It gives the receiving device a way to check the math and verify if the data it just received is exactly what was originally sent. This security guard follows a strict counting protocol. Let's look at the textbook definition. Devices can agree to use even parity. The goal is to ensure the total count of the digit 1 across the byte adds up to an even number. Let's test a sample 7-bit sequence. 1, 0, 1, 1, 0, 0, 1. We count the ones. 1, 2, 3, 4. Since 4 is already an even number, we fill the 8th parity box with a 0. The rule is satisfied. The alternative protocol is odd parity. It uses the exact same mechanic, but this time the total count of ones must equal an odd number. Scanning the sequence here, we can see exactly 2 ones. Let's test your understanding. Pause the video for a second. Based on the odd parity rule, does that 8th bit need to be a 0 or a 1? To hit an odd total, the system adds a 1 to the end of the byte. That brings our final count of ones to 3, perfectly matching the odd parity rule. There is one strict requirement for this system. The sending computer and the receiving computer have to agree on whether they are using the even rule or the odd rule before any data is transmitted. Let's see what happens when things go wrong. Our complete odd parity byte is transmitted across the network. Mid-transit, a power surge hits the cable. The interference causes a bit flip, turning 1 0 into a 1. When the receiving device collects the byte, it doesn't just accept it blindly. It runs a scan, counting up the ones to verify the data against the agreed-upon rule. In this case, it counts 4 ones. The devices agreed to odd parity, but 4 is an even number. The math doesn't check out, which tells the receiver that the data has been corrupted. There is a catch here. The parity bit acts as an alarm system, but it only tracks the total count. It has absolutely no way of knowing exactly which of those 8 bits flipped during the journey. Because the computer can detect the error but can't isolate and correct it, it has to delete the bad data and send a request back to the sender to transmit the whole package again. So the process boils down to a clear 3-step cycle. The sender adds a parity bit based on the rule, the data is sent, and the receiver checks the final count. And that cycle only functions correctly if there is a digital handshake up front, confirming whether they are checking for an even total or an odd total. It won't fix broken data on its own. But by immediately flagging errors the moment they arrive, that single extra bit serves as a vital first line of defense to keep network data accurate.